right, let's get started. Hello, everybody. Glad you could all make it here today. This is our first meeting for 2022. And welcome all you here this evening, even though the weather looks pretty nice out there. It may be tempting to go out and do the outdoor thing. Again, my name is Pradeep Kumar. I'm the chair for the Oregon chapter of the COM Society. And with me, and who will be our host, is Rad Wanatambi. He's been the vice chair, and he's also a fellow IEEE fellow and works for Intel. And I'll hand it over to Raf to bring us to introduce the speakers. Thank you.
Thank you, Pradeep. So you can hear me, right?
Yes.
Oh, okay. All right. So today, we have a wonderful distinguished lecturer. So I'm very happy to introduce our speaker today, Dr. Bilab Sikdar. He is an associate professor currently in the Department of Electrical and Computer Engineering at the National University of Singapore, where he also serves as the Vice Dean in the Faculty of Engineering. He received his bachelor's degree in Electronics and Communications Engineering from Northeastern Hill University, Shillong, India in '96, and the master's degree in Electrical Engineering from the Indian Institute of Technology, Kanpur, India in '98, and the PhD degree in Electrical Engineering from the Rensselaer Polytechnic Institute, New York, in 2001. He was an assistant professor from 2001 to 2007 and associate professor from 2007 to 2013 in the Department of Electrical, Computer and System Engineering at the same university where he got his PhD, which is Rensselaer Polytechnic Institute. He is a recipient of several prestigious awards, including NSF Career Award and Tan Chin Tuan Fellowship from NTU Singapore and Leiv Erikson Fellowship from the Research Council of Norway. His research interests include IoT and cyber physical system security, network security, network performance, and evaluation. He has served as an associate editor in many journals, including IEEE Transactions on the Communications, Transaction on Mobile Computing, and IEEE Internet of Things Journal. He is currently a Communication Society Distinguished Lecturer. He agreed to give a talk for us today. Without any further ado, let's welcome our speaker. Thank you.
Yeah, thank you very much, Rat, and thank you very much, Pradeep, for inviting me for the talk here today. So today the topic is, so I'm going to speak about security and privacy for the Internet of Things. So basically what I'll do is in the first half of the talk, I'll speak in more general terms about, what are the various security issues with IoT at a fairly higher level. And then the second half, I will focus on one specific problem that is related to physical security of IoT devices and how it might be solved. So
sorry to interrupt, Biplab. Is it okay for anybody to interrupt you and ask questions?
Absolutely.
Okay. All right. So
anytime,
yeah. Okay. So anybody want to ask a question? Please interrupt and ask. If that become too many, we will control. Otherwise, please go ahead. Thank you.
Yeah,
Sorry for disturbing.
Not a problem. Yeah. Thanks. All right. So the internet sort of started roughly 50 some years ago, 52, 53 years ago. And when it first started, there were just 4 computers connected on it, and they were primarily in the west coast of US. 3 in California and 1 in Utah. And this is a picture of Leonard Kleinrock standing in front of his router. And back then, remote login was one of the main applications where people really didn't have their own personal computers. You, an organization such as a university, might have a mainframe, and then you would remotely log in. So you would type your username and password. So you'd say login to start with. And in this case, one of Kleinrock's collaborators, or I guess group members, Charlie Klein, attempted to log in from UCLA to the Stanford Research Institute. So he sent an L, it was all right. And then he sent an, sorry, let me move this guy on top. So he wrote, he typed L, and that was okay. O was also okay. But when he typed G, then the whole thing crashed, right? So that's a very humble beginning for the internet. And starting from there, with starting from 4 computers in the West Coast, now we have the internet encompasses the whole world, and then we have billions of devices on it. Right? If you look at the common applications that we started off with, I was talking about remote login. So Telnet used to be the application for that. And back in the early 70s, email was about 3/4 of all the network traffic. Right? FTP was a common protocol, but people didn't have storage, so you would have to constantly move files around, maybe. And then what we are doing now, talking over the network, something similar. The network voice protocol was again back in the 70s, and there were other applications. And the whole thing that changed, but these users for these applications were mainly in the academia, or maybe military, or maybe some research organizations. What really brought the internet to the public domain was in the early 90s, when Tim Berners-Lee invented HTTP. Right? And what this did is it made it very easy to search and visualize information. Right? And then that started the whole thing about internet commerce, social media, and more recently about sharing economy and so on. Right? So if you sort of look at the evolution of how we have been using the network, so there's the pre-internet era when you're talking about phones and so on. And in the early 90s, we had the internet of content in some sense. And here people got into looking for information on the web, reading news, emails, and so on. And in the late 90s, early 2000s, we moved into the Internet of Services. And here people realized that they can use this connectivity to boost productivity, to sell things via Amazon. That's when Amazon and eBay started becoming popular. In the mid 2000s, it was the so-called Internet of People, and this is where Facebook, Skype, YouTube sort of took off, and people started creating their own content and so on. And now we are at the era of the Internet of Things, and the biggest thing here is that, so if you look at all of the early 3 generations, the content, the services, and the people, if you look at who is talking over the network, at least on one end, there's a human involved. It's a human who sends an email. It's a human who downloads something from the web. It's a human who watches a YouTube video. But now our devices are smart enough, are intelligent enough, so they can decide autonomously on their own when they need to transfer data, how to process the data, how to consume that data. Right? And this is the Internet of Things, where we have sort of taken the human out of the loop, and our devices themselves are smart enough to collect, process, and then act based on data. It has enabled a lot of different things. So a simple example might be in the context of smart grids. So even now, I guess in most places you have a meter at home where which counts how much electricity or power you've consumed. And at the end of the month, somebody comes in and looks at how much power, and then you get a bill in the mail, right? But if you're a power generation or if you're a utility company, what you're interested in is knowing that, how much are people consuming, because that tells them how much they need to generate. And it turns out that the power consumption over in a certain region, maybe Oregon or Singapore, it's not constant throughout the day, right? It changes depending upon the time of the day and the weather and other things. So ideally, what the power grid or the utility would like to know is have a very fine-grained idea about how much power is going to be consumed in the next half an hour or 1 hour. Right? So the monthly reading that they get about the power consumption in a household or in an office, that's too coarse. That doesn't give them enough information. But if I can install a smart meter in every residential or commercial unit, and then program it to send me the power consumption data every 5 minutes, 10 minutes, or 30 minutes, whatever it is, then as a utility, I get a much more finer picture of what is the power consumption at this moment, and then I can ramp up or ramp down my generation accordingly. So this would be just one simple example of how IoT can transform our businesses and our lives and so on. So if you look at how IoT is being deployed, so this is from a few years ago, but the trends are sort of still the same. Most of the deployments of IoT seem to be in the smart city and the industry, connected buildings and energy and so on. Right? So all this is picking up. And if you look at different projections about which are the technologies that will play an important part in our economy, usually IoT will land up quite high in the list, and they'll talk about trillions or at least a few $100 billion worth of contribution to the economy. Now, while all of this is good in terms of the potential for IoT to transform our industries and our lives, there are still a few concerns that stop many people from adopting these. And the biggest here is the security concern associated with IoT. And there have been many things in the news that have come up over the years. And the most famous, at least one of the most famous ones is the one in Iran. So there's a nuclear power plant in I think it's Natanz in Iran. And back in about, I think 2011, that got hit by a malware. And what that did is it took over their centrifuges and started spinning them, and they went out of control, and the centrifuges were all damaged. Some people estimate that it put Iran's nuclear program behind by maybe 10 years or at least 5 years. No one claims any responsibility for it, but anyway, and that's one example of how and the industry can get affected. Ukraine, even though it's in the news, it's in big time in the news now, but earlier in 2015 and 2016, when Russia came in and sort of annexed the region of Crimea, in the middle of December, a few regions of Ukraine, their power grid got hacked, and whoever came in, Ukraine says somebody, and whoever they point the finger to, they say that they didn't do it. But anyway, so the hackers got into the Ukrainian power grid, and then they turned off a few of their circuit breakers. As a result, few of the regions in eastern Ukraine, they were left out of power. And this happened in 2 successive years, 15 as well as in 16. And now we hear about ransomwares and other things hitting lots of different places. I think a few months ago, a pipeline in East Coast got hit. This is an example of Lansing, Michigan, where their their water and electricity bureau, or whatever they call it, they got hit by ransomware, and they had to pay to get their files back. And another attack was on Saudi Aramco. So Aramco is the largest oil producer in the world. And I think back in 2013 or 2012, they got hit by a malware. And what that did is it crashed all their hard disks. So overnight, Aramco had to switch over to using faxes and telephones for communication. And they sort of came in and bought up all the hard disks that they could find in the market to replace these back in 2013. So if you're in the market for hard disks in late 2013, you would have seen that the prices had gone up. And one of the reasons for that was Aramco was buying up everything that they could find. and also other things like flooding in Thailand, which affected. But yeah, that's right. So while these examples were more about industrial systems getting hit by cyber attacks, if you think about more mundane IoT devices that you would find in our homes, here's a more recent attack that targeted such IoT devices. And in this case, this was a denial of service, a distributed denial of service attack on a DNS service provider called DIN. So just to refresh the memory of people who might have forgotten what a DNS service does. So for us humans, we tend to remember names such as, Amazon.com or Twitter.com or PayPal.com. But computers would work on the basis of IP addresses. And IP addresses can be either 32 bits or 128 bits, depending upon the version. But for us humans, it's very difficult to remember 32-bit binary numbers or 128-bit binary numbers. So a domain name service or DNS, it translates human readable names such as Amazon.com to their equivalent IP addresses or the binary numbers. So every time we go to a website, we type the name, let's say Amazon.com, and I hit enter. The first thing that happens in the background is my browser does a DNS lookup, gets the IP address, and then it can open the TCP connection with the Amazon web server. Now, this denial of service attack, focused on one of these DNS service providers. So they sent so much traffic that the DNS servers were overwhelmed at DIN, and lots of customers who were trying to get their translations for IP addresses done for these, Twitter, Reddit, Amazon, and they were unable to get their translations done, and as a result, effectively they could not access these websites. And the way this was done is, when you want to launch a denial of service attack, you're basically looking for devices or computers that can generate a lot of data. You want to overwhelm the target with a lot of data, right? So in this case, the attackers were looking for webcams, DVRs, basically things related to video, because video tends to generate high data rates. So their modus operandi was this. So they would somehow find initially a bot that they could get in. Maybe they knew a vulnerability or something. So they would get into the bot. And once they have their foothold in a bot, they would use it to scan for other victims in the network. And once they find a new victim, usually they would try to brute force their way into it. Brute force means, they would try different combinations of usernames and passwords and then dictionary attacks and so on, and then they would try to get in. Once they find a new victim, they send a report back to the report server. So this part is controlled by the attacker. So a report goes back to the report server, and the attacker also has a command and control server. And what the command and control server does is occasionally it will go to the report server and see if there are new victims that have been found. Once it has these reports available, the command and control server sends a command to another computer, which is the loader, and this has the actual malicious binary that will take over the bot and then direct its traffic to the victim. So the malicious binary is now loaded onto the new victim. So by repeating this process, now you have a botnet. You have an army of these bots available for you, ready for action whenever you wanted to. And on the day that you want to launch the attack, the attacker sends a command to all the victims, and then they redirect their traffic, in this case to the DIN server, and that's overwhelmed with the traffic and basically a successful distributed denial of service attack. So in this case, you might imagine that how were they getting into all of these? And there are many, and this is where one of the the shortcomings of many existing IoT devices comes in. In many of our devices, and this was one of the webcams that they actually hacked in. I'm not mentioning the name here, but for this particular device, it had a hard-coded username and a hard-coded password. So the username was root, and the password was always XC3511. So if you had one of these devices, you knew what the username and password was, and you couldn't change it even if you wanted to. And if your friend had one of these same cameras, or if you could find any other person in the world who owned the same model of the camera, you also knew that the username was this and the password was the same, because it's hard coded into the device firmware. And people have demonstrated, this is just one example, and then the people have demonstrated that it's possible to hack into many other things. And some time back there was a well-known attack demonstration where a couple of people, they hacked into a Jeep Cherokee, right? And then they took over the Jeep, and then they drove it over the highway and to the side of the highway and then shut it down. So there are many such examples of IoT devices being compromised and being taken over. Right? So hopefully I have motivated that security in IoT is a serious concern. So now maybe let's look at what does it mean to secure an IoT device. Right? What are the things we need to keep in mind? So traditionally we have the CIA of security for computer systems. And sometimes it's confidentiality, integrity, or authentication. Sometimes it's confidentiality, integrity, and availability. But authentication basically says you prove the identity of the person or of the device that it's claiming to be. Integrity says if you are sending any messages on the network, nobody should be able to change the contents of the message, or even if they do change something, at least you will be able to know that the thing has been tampered with, so you don't take it seriously. And then the last one is confidentiality, which is basically to say if you're sending any information over the network, nobody else other than the intended receiver should be able to understand the contents of that message. So essentially you do encryption. So we still need these for IoT devices. There's no change. However, one of the things that changes from our traditional laptops, desktops, and even your smartphones is many of the IoT devices are much more lightweight in the sense that their processors are not as powerful. They may have a simple 8-bit or 16-bit microcontroller running on there. So they may not be capable of running the same algorithms with same complexity. Or even if they're able to, you may not want to run it on those devices because they may be battery powered. And they're not the same battery powered as your phone, which you can go back home and recharge. The batteries in your IoT devices, it's a hassle to replace those batteries. So ideally, you want to deploy an IoT device and hope that it'll run for 2, 3, 4, 5 years and not have to deal with changing batteries. Right? So any security protocol that you implement should be computationally lightweight, as well as it shouldn't consume too much of your energy resources. Another important thing that comes up with IoT is about privacy, right? So if you deploy all these devices out in the open and they're collecting different devices, you may even want to think about your phone as an IoT device because it has so many sensors in there, right? And it's always continuously collecting different kinds of data. So, but coming back to privacy, here's an example of how an IoT application aimed to simplify processes and to improve processes can inadvertently lead to privacy concerns. So here's an example from London in the United Kingdom, and these are smart trash cans or garbage bins or whatever you call it. Right? And these have sensors in them, and those sensors can determine how full that bin is. Right? So if it is full, it can send a signal, and then the cleaners can make a stop, or if it is not full, then the cleaners can skip it. So basically improves the efficiency of the whole process. But this particular bin, it also had a Bluetooth and connection, and what it would do is it would try to pair with everybody passing by, right? So if you had a if the Bluetooth connection on your phone was enabled as you're walking by, this device would try to pair with you, and then it would record your MAC address. So imagine you are walking along the streets of London, and every 100 meters or so, there at the end of every block, at the end every intersection, there's one of these trash cans. And as you walk along, it keeps track of your MAC address, and basically it can track how you're walking around, right? What is the exact path you followed, what time, and so on. So of course there was a concern and public criticism of this, and they had to take this down. So that's a example of how it wasn't really designed to do that, but then a byproduct of this was a privacy concern. And now that like now coming back to the phone part, our phone has lots of sensors. It's generating lots of different data. And then when we sign up for many services, such as even using Google Maps, for example, it gives us a convenience. It tells us the best path to take, but then Google also knows where you are and how you're moving, right? So of course, when you downloaded the app and then you installed it, you clicked accept in most places, and somewhere you transferred the ownership of the data and so on without reading, right? So in many cases, it may not be very clear that who owns the data and what kind of legal rights the other person has to use your data and commercialize that data. And lastly, one of the things which is particular to IoT devices is physical security. So at least with desktops, laptops, and phones, the assumption is that it belongs to you and it stays with you, and nobody else can easily have access. Of course, phones can get stolen or get misplaced, but in general, that's not what that's an exception rather than the rule. But on the other hand, many IoT devices would be deployed in the open, right? You would deploy your, let's say, environmental sensors out in the open, anything to do with traffic on the roads. You would have to deploy those devices out in the open. So if you have put your devices in the open, it's quite easy for somebody to walk by and pick it up or unscrew it and put it in their pockets and steal it. So if that happens, then you have lost your device, and anything you have stored in that device is also gone. So people can open up your IoT device, pry open, look at the circuit board inside, and then maybe read the contents of the memory and other things. So there are issues that arise because of lack of physical security of IoT devices. So in the second half, I will actually talk about how they can one possible solution for addressing this physical security problem. All right. So now maybe we spend a little bit of time to look at some common IoT vulnerabilities and why they would be targeted. So, there are many reasons why IoT devices may be targeted by hackers or by adversaries. One is that they're always on. Always on means they're available 24/7 for attackers to try and get in them. So if you look at my laptop, at least it's probably off maybe 10 hours of the day or 20, at least 12 hours of the day it's off. At night, I turn off my laptop, and then it's not possible for anybody to attack it. But IoT devices are rarely turned off, so it gives a larger window for attackers to attempt. A bigger problem is that many manufacturers, they shy away from security. They prefer their devices to be as easy to use and deploy as possible. So most of the people here are probably engineers or computer science in their background. So maybe we can set up a small device and put in a pretty secure password and so on. But somebody who is not from a technical background, for example, if you take my mother and you ask her, why don't you deploy this? But before you install this IoT device, you have to do a two-factor authentication. You have to set up this, change the settings, change the password. She'll say, I don't care. I don't want to use your device, right? So to increase their market shares and to make sure it's usable by a larger fraction of the people, many manufacturers don't even bother about security. And since there are large numbers of these devices, if you're capable of breaking into one, now you have a foothold into a large number of devices, and that makes it attractive for people trying to, make botnets and so on. Another thing is, one of the ways I can tell if my laptop has been compromised and it's being used for mining Bitcoins is if I see it's running very, very slow, the CPU is becoming very hot, right? By touching, I feel that it's running very hot. Then I know there are things running in the background that shouldn't be. But we rarely interact with our devices, IoT devices like that, right? So we are less likely to notice that something is going on with it. And of course, the data that is being generated by IoT devices that can have monetary value. So that's attractive to various adversaries. So if you look at what are the common vulnerabilities in IoT devices, one of the biggest problems are these, exposed serial ports. So if you open up any IoT device, you will see that in the PCB, in the circuit board, there will be these, different kinds of serial ports which are there. They're unused, but they are still in the PCB. And the reason they are there is because during the manufacture process of this IoT device, they were used for debugging. Right, the manufacturers use these ports to interact with various components on the board, see what's going on. But once the design is complete, you're probably selling these IoT devices for $10 or very, very small values, right? So the margin isn't very large here. So so manufacturers will try to cut down the cost as much as possible. So you don't want to redesign another PCB here. So they leave the original ports in there. They just don't connect anything. But if you open it up, you will see them. And if they are there, you can easily now connect your wires here, and then you can read off things from the memory or interact with the CPU and other things. And there are a lot of different people have demonstrated how they can use these exposed serial ports to extract secrets from the IoT devices. Let me erase this there. The other thing is about hard-coded or default or weak credentials. This is one of the examples that I was showing you when I was talking about the Mirai botnet, the attack on the DNS servers. Sometimes it may not just be the IoT device itself. We usually interact with our IoT devices through web apps or mobile apps. Sometimes the vulnerability is in the mobile app or in the web app. IoT devices tend to be limited in terms of their CPU and energy resources, and encryption, use of security mechanisms. They all consume some energy, right? So so if you think about it, it's an overhead. I can send data in plain text, costs less energy. I can always encrypt it, make it more secure, but that's going to cost me more energy. So in many cases, IoT device manufacturers will say, okay, don't care about encryption because then my device can run longer. They'll say, oh, a single battery will last you 2 years. So it's a trade-off. In many cases, IoT devices don't care about integrity checks on messages or verifying the signatures of software that they get. So for example, there are many IoT devices where you can upload a firmware and it will not check to see if the firmware is really from the manufacturer of the device itself. So there's no signature verification and so on. And while it's fairly straightforward to update the firmware or the operating system on your desktops, laptops, and so on, with IoT devices, it's not so easy. And not just that it's not easy, in many cases, vendors don't really provide support for repairing vulnerabilities. There are many well-known cases where vulnerabilities are reported to the manufacturers of the device, and they take 12 months to 2 years to repair those vulnerabilities. And in many cases, the manufacturers will have the mentality that, my next generation product is going to come up in 6 months or 1 year, and then I'm going to, removes support for my older generation anyway. So I don't want to bother patching the vulnerabilities that exist. So that's a common attitude that's taken. And of course, coding errors are always possible with any software system. And then the physical vulnerabilities that I was just talking about. And then, in terms of security challenges, the usual challenges are there's a large number of identical devices. So when there's a vulnerability identified for one, a large number of devices get vulnerable. There's usually no user interface with IoT devices, so it's more difficult to see what's going on and to interact with the device. And sometimes you may have a patch available, but the IoT device may be used in an application which is running a very, very critical service, and you cannot have any downtime. So in those cases, the operators or the users of those devices will say, it's okay, I need to, I cannot afford any downtime for my system. So after I patch, I don't know what's going to happen, whether it's going to boot up properly, things will be fine or not. So I'm not going to take that risk. I will not update my system. And this is actually fairly common in the old, such as power grids, where people are still running Windows NT and other operating systems. And then the other parts about limited computing and battery and so on. So if I have to secure an IoT system, then what are the things I should be worrying about? There are many different things. Of course, you need to have a framework for handling data. So there needs to be control over the sources of the data, as well as the consumers of the data. So basically access management and control of the data. So there needs to be a proper framework in your organization to ensure this. Another big thing is, establishing the trust management system. So what is it how you establish that? So for humans, it's a different scale of problem, and for devices that operate on their own, building in trust in them is a different problem. And in the second half of my talk, I will see how we can use hardware-based trust mechanisms. The other things are, even though it costs us energy, it's still advisable that we should be using secure protocols during communication, encryption, integrity checks, signatures, and so on. In terms of firewalls and antiviruses, so if you had asked me 2-3 years ago, there were hardly any firewalls or antiviruses that were specifically targeted at IoT devices. That's been changing, and there are many new products coming up in the market that that specifically address these problems for IoT environments. And the other thing that is really needed are, more companies need to wake up to the possibility to consider how remote updates and patching of IoT devices can be done. This is something that still probably needs more work. And ultimately, it's not just the device manufacturer or the user. There's a whole ecosystem around starting from the manufacturer to the application. There's a whole number of players that come in, and probably everybody has a role to play to make sure. And this may include the platform operators, the device vendors, the ones making the apps that we use to interact with these IoT devices or applications, all the way to the government and the policymakers, right? And this is something we have been seeing has been happening in many places. EU has put up many different rules. Even here at Singapore, the government is becoming more sensitive to data and security and privacy and things like that. So ultimately, all of these players have to come together and come up with everybody has to play their part. All right, so that was sort of the first part, and then in the next 15-20 minutes, what I'll do is I will talk a little bit more about one specific problem for IoT security, and this is to say how we address the problems of physical security for IoT, right? And just a quick recall that by physical security, what I mean is, IoT devices may be deployed in the open, so people can easily pick up or steal that device and then subject it to different kinds of attacks, right? And the main challenge here is that, when if you think about as a human how you authenticate yourself, for example, you have your username and password. And this username and password you have stored in your own memory, right? So when you check your email, you type your username and you type your password. But for IoT devices, there is no human who will help the device with its username and password. So the secrets, whatever the password is or the username is, that's usually stored in the device itself, in the memory of the device, right? And if your device is stolen, then I can open up and I can take out the memory and I can read the contents, and then I have your username and password. I can connect the wires to some serial or any other ports in the device to read the things in the memory. Or I can also subject to various side channel attacks. For example, there are attacks that have been demonstrated where you can place an antenna on top of the CPU, and as the CPU is running, let's say, an encryption or anything that uses a secret key, by looking at the EM radiation that's coming out of the chip, we can, they can reverse engineer and then come up with the key that was being used. Right? So those things have been demonstrated. So then the question is, how do I keep my device secure even though it can be stolen? And I want to ensure that the secrets are not leaked out. Right? And one option there is to use, a hardware root of trust. So rather than store your secrets, maybe you can use certain characteristics that are inherent in the hardware itself that can be used to uniquely identify a device. So it's sort of like looking at your for humans by looking at your fingerprints or your iris scans. Every human is unique in that way. So maybe we can find something in the hardware of the devices that are unique. And it turns out that during the manufacturing process, even though you control your processes very, very finely, there are still certain randomness that creeps in, and that gives unique characteristics to every single chip that is produced. And the idea is then, can we exploit these to our advantage and use them as fingerprints that provide a hardware root of trust to the device? And these are what are called physical unclonable functions. And physical because they are based on actual physical properties, the wires and the transistors in the device, the physical characteristics of those devices, of those components in the devices. And unclonable in the sense that since they're caused by random things that we cannot control, hopefully you cannot recreate the same conditions a second time. So it's not possible for an adversary to create the same hardware root of trust again. So let me give you an example about what these process variations might be that can lead to this, and how. So I know there are many people, at least Rath is from Intel, and then this is probably quite familiar to people working in the semiconductor industry, but for others, just a quick recap of how a typical integrated circuit may be manufactured. As you start off with a silicon substrate. Let's say you want to create two wires. You start off with a masking film, and then you put a layer of photoresist on top, and then you have a mask which has the imprints of the circuit that you want to create at the end. So you put the mask on top of this, and then you shine some ultraviolet or whatever rays that you have. And then the part that is not covered by the mask, that gets that reacts with that is affected by this ultraviolet rays, and then you go through a process of etching and stripping, and then you end up with the desired circuit that you have, right? And ideally, these are, these days they may be in the order of few tens of nanometers or just a few nanometers or whatever, right? And then if you look at the circuit itself, at the performance, and if I look at how long, maybe in terms of delays, the circuit delay. So one way of looking at the circuit delay is it depends upon the dimensions, right? What is the length of the wires that I have in the circuit? What is the, the physical dimensions of the gates and so on? So when I'm doing all this etching and the whole manufacturing process, this might be my original layout. Maybe I want my wires to be laid in these very nice straight lines with perfect 90-degree angles between them. But when I'm done with the actual manufacturing process, it's never going to be exactly like that. So finally, my wires and other things may look, they may have some curves and so on. And occasionally they may be, half a nanometer short, half a nanometer long, something. There'll be some variations around it. And this is usually the, so a gate length in the 130 nanometer is usually 90 nanometers, but then we tolerate a variation of about 5 nanometers in there. So the whole basic idea that I'm trying to come up with is that, you start with a particular design that you have in mind. But in the end, after the manufacturing process, there will be some variations in it, right? And then these variations are not really very well controlled. So how can we exploit that to create our security things that we need, right? And here is one example. So here what I have is I have a flip-flop in the end, and then I have 2 rows of multiplexers. Right? I have 2 rows of multiplexers, one on top and one on bottom. And the multiplexers are given the same control or selection bit that I have here. Right? So if we look at every column of multiplexers here, each column gets the same control signal. So here in this column, both the multiplexers are getting a 0. Both the multiplexers here are getting a 0. Both the multiplexers here are getting a 1. Right? So they are controlled by the same thing. And there's a single signal that is feeding into these multiplexers. Now, if you look at this particular example where I've given a 0, 0, and 1. So in this case, in both the multiplexers, the input corresponding to 0 is being selected. In this, again, the input corresponding to 0 is being selected. And here, the input corresponding to 1 is being selected. So at the end, there are 2 signals coming into this multiplexers. There's this blue path, and then there's this red path. So on paper, when I design this, the blue path and the red path are identical in terms of their lengths and the number of devices they're passing through. Right? But they're exactly the same. There's no difference. So if I give a clock pulse here, they should reach the flip-flop at the same time. They will both be delayed by the same, they'll both experience the same propagation delay, and they should arrive at the flip-flop at exactly the same time. But then, like we were talking here, during manufacturing processes, so there will be some random variations. So it'll turn out that either so one of them, we cannot say for sure, but either the blue one or the red one will be shorter. And that'll happen at random. So one of them will be shorter, and if by chance the top path is the shorter one, the flip-flop will register a 1. And if the red path is shorter, we will get a 0. Right? So if I manufacture the same piece of circuit again, there's no guarantee that we will get the same result, right? Because we are not controlling, and next time when I manufacture this, maybe the bottom path is shorter this time. And then what I can also do this is I can take the circuit here, and I can create many different rows of this. So each one of them is a random bit of output. So this control signal that I'm giving here, I call it the challenge. And the bits that I get here, I call it the response. Okay. And this particular chip for a given challenge will give me a certain response. And if I take the same challenge and give it to a different chip with the same circuit, it will give me a different response. Right? So essentially, this becomes my physical unclonable function and the unique fingerprint for the device. So this is the basic idea. So if I have many different chips with the same perf circuit in them, and if I give the same challenge to all of them, they will ideally give me different responses.
Well, mightn't that change by temperature or?
Yes,
like
that's true. So the lengths of these devices are indeed changed. They are dependent on the temperature because they may vary, and so as a result, you may have to do things like at the end of here. One way to handle that is to use, for example, an error correction code. So you have to add an ECC block to this, which will sort of compensate for those errors. And this is this is a very simple example of creating these puffs. There are other designs also. So for example, if you have a DRAM, you have to refresh the DRAM every whatever few tens of milliseconds or something. And if you don't, then they will give you random bits, and they will lose the memory. So there are other things that are less sensitive to memory. They're less sensitive to environmental factors, but they also give you equivalent unclonable properties. But yeah, you're absolutely right that this is indeed dependent on temperature, and then also the voltages and so on. So some additional things here need to be in place to ensure that the response that you get is independent of the operating conditions. Yeah. So puffs have various different advantages, and some are listed here. So they tend to be a little bit more secure against timing attacks. Mainly, they're more secure against side channel attacks, power monitoring, and EM attacks, and so on. So personally, I don't make these puffs. I'm not a hardware person. I have a colleague who makes them. But what we do is we build security protocols that exploit these puffs. And one example that I will do here is to how we can do authentication based on puffs. Okay? And the idea is that there's some basic assumptions about puff. So for example, if you physically tamper with the puff, it destroys it or it changes the property. You cannot accurately model or clone a puff and so on. What we will assume here is that the IoT devices may be constrained, but the servers have no such limitations. The IoT devices are unprotected and they can be accessible by any adversary. And then the standard things about, when you do authentication protocols like this, that the adversary can eavesdrop, modify, inject, and replay messages and so on. Right? So this is just notation in case you're. So this is a very simple, I simplified the protocol quite a bit so we can go over it easily. And basically 3 steps. Okay? But before the actual authentication protocol starts off, what we need to do is there needs to be a registration process where for this particular IoT device, I will give a challenge, that's a CI. I will observe what is the response, RI. And then that somehow has to be, when you're deploying the thing in the open, for the first time, you have to update your server, maybe through a secure channel or through a backend. The registration process has to be done. So the server also has this CI and RI stored in its memory. For that particular device, it will say, okay, IoT device ID, this is the A, and this is your challenge, and this is the corresponding response. The server has stored it in its memory. Okay, so now let's see how the device will authenticate itself. And we have 3 steps here, and then I will blow up these steps in a bit. So in the first part, what the IoT device will do is it will send its identity, and it will generate a random nonce, and it will send to the server. So the server sees, okay, somebody claiming to be device A wants to authenticate with me. So it will read the challenge response pair for that IoT device, the challenge CI and RI. And then it generates its own nonce, and then it will send a message back to the device, which will have its ID. It will reply back the nonce. It will add its own nonce, but all of this will be encrypted using this response. Okay? Maybe this is a 32-bit, 128-bit, or whatever. You use it as the encryption key, and then you encrypt it. So you send this encrypted message over the network. So you send this encrypted message, and the challenge itself you can send in plain text. No one, that doesn't affect. And then you also send in a message authentication code to verify the integrity of the message when it comes to the other side. At the IoT device, it will take the challenge and it will pass it through its puff. So once it passes the challenge through its puff, it can get the response. Anybody else, if the adversary gets this particular message, they know the challenge, they can pass it through their own puff. But since every puff is unique, they will get a different response. And as a result, they will not be able to decrypt this message. So that's essentially the security part that's coming in. So once it has obtained, the device has obtained the response, it can decrypt the message, MA, and it can get, once it has decrypted, it can get everything in here. And what we also want is we don't want to keep using the same challenge and response again and again and again. So what we do is in every iteration, we change the challenge to a new value and we use a corresponding response. So the device generates the challenge that we will use for the next round based on the nonces from the 2 sides. And then it passes the challenge through its puff and gets the new response to be used in the next round of authentication. But this is at the device end. It needs to communicate that back to the server. And also it needs to, complete the authentication with the server. So it takes the nonce that was sent by the server, encrypts it using RI, and it will also encrypt the new response to be used in the next round, and then send it back. And the server can decrypt this message because it already has RI. And once it decrypts, it can get the response to be used for the next round of authentication. And it can also create what is the challenge to be used for the next round of authentication. Okay. So there's a very simple example of a protocol that can use puffs to do mutual authentication. And once you have this, you can go through, you need to prove that your protocol works. So there are things that you will want to show that the protocol is complete. That means it will take all valid inputs. It's free of deadlocks. There will be it will not get stuck in an infinite loop, and then it will terminate properly, and properties like this. And then there are various proofs for showing this, right? So my intention was not to go through these proofs, but just have it because I'll share the slides later on. So just in case somebody's interested in this. And now I was talking about my colleague who makes these puffs. So along with him, we created a system on chip for sort of like an IoT device, which has a Zigbee radio, and then it has a hardware security subsystem where we do have a puff. And then, there was a question earlier about the stability of the puff and so on. So there's an ECC in front, and then it's followed by our crypto core, which does all the encryption and the MAC and then other things. So just to then, this was more of a proof of concept. And here we have the energy that is consumed by different, things that the different subsystems. And of course, the wireless is the one that takes up the most energy here. And these are some, very, very intuitive results that show, how much energy we consume as a function of the number of bits in my challenge and response. So of course, if I use more bits in my challenge and response, the whole thing is a bit more secure, but then you pay the price in terms of the energy that you consume. And this one is the x-axis shows for different sizes of the challenge response pairs, and also how many bits that you're sending in your messages that you're exchanging. Of course, if you have more bits in the message, you'll spend more energy. And this is for the radio part, again, similar trends. And then, coming sort of to while I was telling you the use of puffs for security, puffs are not, completely free of issues. One of them was already raised, that, puffs can be quite sensitive to environmental factors. So bits may flip when the temperature changes, for example. So one option there is to use ECC and other things. You can also use, what are called fuzzy extractors to sort of stabilize and take care of errors, but they come with an overhead. But more recently, the bigger problem with puffs has been, machine learning attacks on puffs. So while I may not be able to open up a puff and look at what's inside, but if I get enough challenge response pairs, if I have a large number of these, I can feed it into a machine learning model. And then hopefully the machine learning model, if I give it a new challenge which has never been seen before, it can hopefully give me the response. And the puff design that I was showing you earlier, that's what is called an arbiter puff. People have shown that arbiter puffs are already, they're susceptible to machine learning attacks. So then the more recent work that goes on is how do you come up with puff designs that are more that are secure against machine learning. So anyway, so that's sort of the end of my talk. So what I wanted to present here is a high-level overview of security challenges for IoT and what is required to solve these problems. And in particular, we looked at puffs as one promising solution that can provide us with, a solution for at least the physical attacks on IoT devices. So again, thank you very much to the IEEE ComSoc Oregon section for inviting me, especially Rath and Pradeep. Thank you.
Thank you, Biplab, for a very interesting talk. I have a couple of questions, but let's wait for any other questions from the audience.
Sure.
Please unmute and you may ask if you have any questions. Maybe I'll start one. I think you already, somebody asked a question, and also you touched upon the impact of weather and things like that, right? So my question is the misdetection. You cannot even identify your own device. That can be a problem.
Yes.
So did you do any analysis on that, or
yeah,
in different cases?
No, but I think there are the people who make these puffs. They subject their puffs to operating conditions starting from -30 to about +60 degrees Celsius. And I think these days they can bring down the bit error rates to less than 1%. And then if you follow that up with a error correction ECC block, then the overall the likelihood that you will not be able to detect your own device, I would think that it's going to be fairly small. But yeah, it's not zero, but probably you can live with it.
I see. The idea is to bring the number of errors to be small enough that you can correct with the error correcting code.
Right. And then error correction ECC also costs you silicon as well as power. So you want that to be small. So I think what my colleagues and they try to do is they try to somehow minimize the bit errors themselves. So they don't need so much ECC.
How about the effects of EMI?
Yeah, again for that I have seen some people EMI probably not as effective at clipping the bits as temperature and the supply voltage. But then again, some people propose to use inside the chip itself to have a wire mesh of some kind, which will protect the thing from EMI. But yeah.
I mean, one of the easier ways to attack this is with a vibrator. Right, you're going to cause phonons inside of your structure. And now I might not be able to break into your system, but I can prevent you from getting on your system.
Right. No, I agree with that. Yeah. So I don't think people have looked at solving or that kind of an attack and how to. Yeah. But if you're vibrating and so on, I don't think this is. If you're capable of launching those attacks, I don't think there is any known security solution for puffs for those things.
Why is this any different than just loading it up with some traditional encryption where you're essentially doing a one-time pad and just using it that way, right? Yeah. I mean, you can randomly load your key space into your lattice. Then you don't need to depend on the puff. Everybody can build it the same, and it can randomly generate it so that the vendor never sees access, but you can still use it, and you're actually using real semiconductor processes and all of this experience that we have over the last many decades for error correction and everything else. You still get to use something that's specific. You can burn it in one time. That's essentially what you're doing with the puff. Then you can go lower power.
Yeah. Yeah, I don't really have a answer to that. Not. So you're saying that will be lower power than puffs.
Think about it, right? If you've got some traditional, pick your favorite encryption method, and you need to load it with a key. Okay, because what you're doing is challenge response every time. Yeah. That way I can load it with my own key. I know what the challenge response is going to be, and I've got all of the key it's a cyclic key anyways. All of these are cyclic that we're describing. You might as well just load it with your own as opposed to let it randomly generate it, because you can randomly generate a key space better than you can with the process. Right.
Sure, but
and then it gets loaded once, burned in, and now it's the same. And all your.
Then if somebody has physical access to your device, would they be able to read that?
The same way, if I have physical access to your device, I'm going to read your puff anyways.
You cannot read my puff. You can give it a challenge.
So the direct read of the puff or just sending stuff through it is the same.
Direct.
If I can hide my key in some complex structure, right? I burn it once randomly, right? The one-time key is in the structure. You can't read it directly because there's no arbitrary place for it to live. It's the same as your puff, and now I just send bits through and apply machine learning until I get the answer, and it's the same. It's exactly the same, and my key space is better than the randomized key space of production.
I would have to look into that to really be able to comment on the exact which one will perform better. But What I can say here is that the challenge space for puffs, again, you're not constrained. You can, well, in my protocol there, you're randomly generating the nonces. So essentially, every time that you're creating the new challenge, it's generated completely randomly. Well, as long as you're as good as your random number generator is, I guess, on the system.
I was giving you, hey, I had a perfect random number generator.
Okay.
Right.
Yeah.
You got a perfect random number generator, and think about it this way, right? Your puff has a big architecture where there's a slight changes in the delay lines across your matrix, right? Those you're depending on those for manufacturing.
Yep.
Right. They're fixed. Ideally, they're fixed, right?
They're fixed, yeah.
There's no difference in that. And then you just randomly programming some of those legs to be longer than others. Exactly the same. Right. But you get to do it
exactly the same.
Yes, but I get to do it with good random values distributed across your entire space. Whereas you're depending on a process
things
to be
happening
random.
at random, yeah.
Right, which doesn't guarantee a good space.
Okay.
Just to interrupt to understand. So is that the idea is to, so I thought, you are using the, okay. The puff is, something you are introducing, or you are using the randomness already there?
So I am making these circuits, but I'm not controlling.
Okay, so you are introducing. Okay, all right,
yes.
right. And then, the question is asking is, like, why don't you do in certain way that can
right.
Okay.
Right. He's saying that I'm random. I'm waiting for randomness to decide which one of these is longer.
Right.
And he's saying that let's program this to be longer by picking at random.
Right. Yeah.
And you can do that after the fact, after manufacturing.
Yeah. Thanks for the idea. I think it's worth looking into it. Yeah.
Interesting point. Yeah. Any other?
Just give me some credit.
Yeah. Absolutely.
Anybody going to file a patent on this?
I think it's past that at this point, isn't it?
Yeah, it's past.
Public discussion.
I think this particular circuit is from 2005 or 4 or something.
Right.
Okay. Any other questions from audience? I have one other general question. So, you talked about a lot of security issues for IoT, and talked about this, physical layer. Some people call it physical layer security, and you call it physical security, whatever.
Yeah.
So this is one area of research going on. It's in one way it's hot topic. What are the major effort taken by the industry or academia and industry on resolving this IoT?
Hello?
We lost him for a minute. Raf, we can't hear you.
Security issues.
Raf, we can't hear you.
Okay. Can you hear me or not?
In the middle, we lost you for.
Oh, really? Sen, it's a problem in my side. I thought, it's a problem in something else. I will ask the question again. You can hear now, right?
Yeah.
Okay. Yeah. It's basically, I was mentioning, like, you talked about a lot of security problems for IoT, and then, one research area and solutions you talked about, right? So what are the other, since this is a big problem, in addition to this physical layer security, what other research efforts are going on to resolve, say, security for IoT?
Yeah. So I think many of the telcos and other, security service providers, they are increasingly coming up with firewalls and intrusion detection systems that are specifically targeted at IoT environments or industrial control system environments. So traditionally, they would be more for an IT enterprise environment, and now there are products coming up that look at different kinds of intrusions in ICS or IoT settings. I think that's probably the biggest change that is happening, and then this is coming up, opening up as a market. Another way that many researchers are looking at is because IoT is being used for controlling physical things, right? And the cyber physical systems, let's say, they are governed by some laws of physics. So there's also this move towards looking at physics-based anomaly detection or physics-based intrusion or detection of attacks, where you say that your IoT or any sensor or anything that you've deployed is saying this, but is it even possible by the laws of physics? So that's another area that's becoming quite a lot of people have started looking at that. Especially maybe in the field of smart grids and more of industrial systems.
Let's see. Okay.
So I have a question. How do you authenticate real inexpensive sensors? For example, just something that's a resistive sensor, and you don't want to have a processor in it. Are there techniques of being able to do that?
Yes, if you have a processor in them, then currently
you don't have a processor.
You don't have a So in
Right.
this case, yeah, if you don't have it, then it's difficult. But then there are some other ways in which people do is though these are more of academic research. I don't think they exist in as a product as such. So one way to say is to look at the device fingerprint more from the wireless transmission part of things. So I know that, let's say these devices would be communicating, let's say through a wireless gateway of some kind. And at that wireless gateway, I would collect some information related to, when this device usually communicates with me. This is the signal strength. This is the usual, whatever physical layer characteristics of that system, of the transmission. Now, if somebody else is pretending to be that device and communicating with me, then at the physical layer, do I get the same kind of signals? Is the signal strength the same? Sometimes they also look at the clock, at the clock with which the symbols at the physical layer are encoded and so on. So you could sort of passively authenticate these devices by looking at some other features from based on their communication patterns. But yeah, other than that, I am not aware of anything that you can use to directly authenticate that device.
All right. Any other questions to Biplab? Sorry.
Well, it's okay.
All right. If there is no other questions, let's thank our speaker for a very insightful talk. Thank you so much, Biplab.
Okay.
Next time, hopefully, we can see, you were asking, like, you are coming to US in March time frame. Do we want to do a face-to-face? Not yet. Maybe next time, next year, we'll see.
Sure.
Yeah,
absolutely. Okay.
Thank you very much.
Thank you all for coming today. Yeah.
Thank you all, and have a very
Thank you so much. Okay. All right.